So when we started off earlier in the morning, John Wright was talking about inverse problems and compressed sensing, and that's where we began. And so to top it off, this last talk will take us back to inverse problems in sparsity and connections to deep, and then on to deep learning with a focus on imaging. So just a quick shout out to my group. Many of my members are here who contribute. Some of them contributed to the works in this talk. I'll cover some background in the beginning, and then I'll be talking more about our very recent research for most of the talk. Firstly, starting with supervised learning of sparse models and sort of regularizers in inverse problems, and learning these regularizers in a supervised way. And then I'll move on to learning regularizers with no supervision and with no training data. And then the last part of the talk is going to be going back to supervised learning, but then focusing on building robustness into the learned networks for image reconstruction. So here are a bunch of images from different imaging modalities. There are lots of different imaging modalities out there. MRI, X-ray CT, ultrasound, different kinds of microscopy, to name a few. And in all of these imaging systems, it's often not trivial how you form these images from the data that's collected. So an important goal sort of in computational imaging is to form images from the collected measurements of the data, measurements of the images. And these are often indirect measurements rather than direct pixels of images like you observe in your camera. And often the objects you're imaging are not discretized. They are continuous functions. But then for our purposes, when we do image formation, we discretize these images onto pixel grids. And image reconstruction is important in a lot of applications in medical imaging, in material science, in physics applications, in astronomy. For example, the algorithms that went into making images of the black holes that we heard about in the news in the past came from sophisticated image reconstruction algorithms. And typically, these algorithms rely on a model of the imaging process so that you have an image X you're trying to estimate, but you only observe the measurements Y. And a simple measurement model is a linear model connecting the image X and the measurements Y by a measurement operator A. And on top of that, there may be some noise in the process. So the H denotes the noise. So even for a simple linear model of the imaging process, there can be complexities in recovering the image from those measurements Y. So for example, a simple way to reconstruct the image X would be by solving a least squares minimization, where you minimize the difference between Y and AX. AX is the representation from the imaging model of the measurements. And you can solve this least squares problem by using your standard tools, compute a pseudo inverse, or do conjugate gradients. But the challenge is that many image reconstruction problems in the real world are ill-posed, so the solution may not be unique, for example, or they are ill-conditioned so that the computing the pseudo inverse would tend to blow up the noise in your data. So here is an example. So this is a cartoonish setup of CT where you have an X-ray source, and that's emitting X-ray photons, and those pass through the object that you're trying to image, and then it hits a bunch of detectors on the other side. And sometimes the source and detector are rotating around the patient, like it's in common medical CT scanners, or if you're imaging materials, the object may be rotating on a table and so on. But every time a set of measurements are collected or projections are collected, you're basically collecting a set of measurements in this Y vector and corresponding to a set of rows in the operator A, or the measurement matrix. And so depending on how many such views you collect, so from different points in the circle, the source will emit X-rays, and you collect measurements. Depending on how many of those angles or views you collect, you can get reconstructions. If you sort of do the pseudo-inverse reconstruction, which is called filter back projection in CT, then if you have enough views or enough locations of the source from where you collect the measurements, from where from wherein you get the measurements, then you can get a good reconstruction. But if you have limited data, then the conventional algorithm gives really bad images. And especially if you have 2 views, 4 views, it's very poor. In fact, I mean, one of my students will talk later in the poster session of how can you learn something that works for this few views. And another example is MRI, where the data is collected in the Fourier space of the object. So think of this as the object. This is the Fourier transform, and then samples of the Fourier transform are collected. And this is done often, in a certain regular manner with a certain sampling trajectory that satisfies Nyquist sampling conditions. And if everything falls in place, you get a good image by computing an inverse Fourier transform of this collected data. But often this process is very slow. So in MRI, you want to, the goal is often to speed up the scan by collecting less data. But if you collect less data, your object may end up being very blurry, or there may be aliasing artifacts if you collect the data incorrectly. And so this kind of led to the field of compressed sensing, where basically you could, folks said you can collect data, but in a sort of undersample the frequencies in a certain random way, and then your image reconstructed by simple inverse Fourier transform turns out to be not as terrible. So these methods that just do the pseudo-inverse kind of reconstruction are not as good as we are seeing in cases when you have limited data, or when you have corruptions in your data, or the imaging operator is not well behaved. So in those cases, it's often useful to impose regularization on top of sort of minimizing a least squares loss. So the least squares loss is, in typical imaging systems, you may have, depending on the imaging physics and the measurement noise model, you can have much more complicated data fidelity functions that are not just least squares terms. And then you impose regularization. So sparsity is a kind of regularization that can be imposed to sort of make the problem more tractable. So you can, if you have infinitely many solutions, you would select the sparsest solution. And so that kind of was a big breakthrough in MRI with compressed sensing, that you could collect fewer measurements, sort of randomly sampled in K-space. These are the red dots, the samples that are collected. So you could collect much fewer measurements and then exploit the sparsity of the image in sort of a wavelet space. This is going back to John Wright's talk. He kind of showed a picture similar as well. And exploit that, and in regularization, and then you could reconstruct the image from much fewer measurements than you would normally collect. So, however, the reconstruction process now is, with this model-based reconstruction, as I called it in the previous slide, is more complex because you need to solve an optimization problem. And depending on the regularizer, whether it's convex or non-convex, you may have issues of how do you initialize and all of those things. So designing these regularizers, there's been a lot of research in imaging on how you would design the regularizers. And going to the theme of this workshop, sparsity, low dimensionality has played a key role in the design of regularizers for these image reconstruction problems. Sparsity as well as low rankness has been exploited heavily. And a common sparsity model is that we assume that there is an operator W, like the wavelet transform, for example, that when applied to your image, sparsifies it. So the L1 norm, as we saw earlier today, is sort of a way to measure sparsity, and it's convex. So you can plug that in as a regularizer, and as long as you know the sparsifying operator, you can solve this optimization using any of the standard tools in convex optimization and kind of get a reconstruction. And more recent works have looked at learning these transforms or dictionaries, and these dictionaries could be, or transforms could be learned from a collection of images, or they could be learned even from noisy data or sort of undersample measurements. So all of that is possible. What we are going to focus on is how can we learn these regularizers in a supervised way. So if I have samples of noisy images and corresponding clean images, can I learn regularizers that when plugged in to this optimization problem would give you the best reconstructions? So that kind of leads us to this sort of a supervised way of learning regularizers, where basically I have a training set of noisy images and clean images. XTs are the clean images. And the goal is to find a sparsifying operator, W, such that the reconstruction that's obtained with it, so you solve an optimization problem and get a reconstruction, and you want to find an operator such that this reconstruction is as close to the ground truth as possible in a sort of, say, for example, a mean squared error sense. So if you kind of stare at this problem, you can see that this is not a standard optimization problem. This is a bi-level optimization because the loss function you're optimizing on the top depends on this quantity xt star, which is coming from a different optimization problem. So, so that's kind of, that makes it a bi-level optimization. And there could be additional regularizers, J of W, like W, you could enforce it to be orthogonal. We saw that coming up in earlier talks. Or there could be sparsity in the weights, like Atlas talked about. So how do we solve this sort of bi-level optimization? So if we look at the literature, so the challenge is that we have to, if you take gradients through the upper level loss function, you need to compute gradients of this X star, which is coming from an optimization. So it's not clear how you compute that gradient because it's not a closed form expression for X star, XT star. Now, there are a few approaches that people have adopted. One of them is unrolling. And so basically, you run an algorithm. I think Yima talked about this. So take an algorithm for the optimization problem, say something like ISTA, and unroll it for many iterations. Often cannot be too many because then you run into memory issues. So unroll it for a few iterations and then kind of use that as a representation of X star and kind of learn the weights in this unrolling. So the issue with this is that you cannot often unroll for too many iterations and you run into vanishing gradients and other issues. And if you run it for unroll for only a finite iterations, then at testing time, it can create issues, as I'll show later in my talk. Another approach is sort of replacing something like the non-smooth L1 norm with a smooth relaxation, like the Huber loss. But then this introduces a relaxation, right? So you lose the exact sparsity property. And also we have observed that if you do the smooth relaxation, the performance also suffers. So we want to really solve the bi-level optimization with a non-smooth regularizer. So the way we are going to do this is derive an implicit expression for the solution of the L1 minimization problem. And then we will look into when that implicit solution becomes explicit, and then that'll lead us to kind of going into a gradient descent algorithm with an explicit expression. So here's kind of the theorem. And what it's saying is that let's assume we know the solution of the minimization problem, the lower level problem. So if we knew the solution, if we have the transform W, we can compute the sign of this W times X star. And this quantity, this vector S, only has the non-zeros in that sign, so only the plus ones and the negative ones. And W0 and W plus minus denote sort of a subset of the rows of W corresponding to the zero components of Wx star and the non-zero components of Wx star. So once we compute the submatrices of W and the sign pattern, then we can actually use KKT conditions or Lagrangian dual analysis to derive an expression for X star in this lower level problem. And the right-hand side, the expression depends on the sign pattern and on the sub-matrices of W. And think about it as, a way to see how you derive this is think about KKT conditions and assume the sign of WX star is known. If the sign of WX star is known, then basically the L1 term can be relaxed to a simple linear term. You can think of it as the sign pattern or the sign vector transpose WX because you know the sign. Then that leads to simplifications from which you can derive a closed form expression. This is an implicit expression and not explicit because the right-hand side depends on X star as well. Because the sign pattern, W0, W plus minus, all depend on the sign of WX star, which depends on X star. So that's why it's an implicit closed form expression and not an explicit closed form expression. So how do we make this an explicit closed form expression so that we can compute gradients and learn a transform? So here's an example. So consider a scalar denoising problem where everything is scalar. We have a scalar y, which is noisy version of x, and w, our transform, is also a scalar. And if we kind of write out the lower level loss function, we can write the solution explicitly because it's a scalar optimization. And it turns out that in this scalar setting, the x star kind of looks like this triangle, and y here is sort of the noisy signal. And if you look at the sign of WX star in the simple case, the sign of WX star turns out to be piecewise constant. So there are regions where it's +1, -1, +1, or 0. And what that means is that the sign of WX star, so that's what this is. Sign of WX star is piecewise constant. So there are regions where the sign is fixed. And if the sign is constant in those regions, the implicit closed form expression becomes explicit. Because if you fix the sign pattern, everything on the right-hand side is fixed. So it becomes an explicit function of W, and then you can compute gradients of X star with respect to W. So that's kind of the trick. And so if you look at the loss function Q of W for this one-dimensional problem, it's not a convex loss. It's not convex. It's not smooth. It has multiple minimizers. Apparently, it turns out those minimizers are kind of equivalent. They have the same loss function, but this is not, we have observed empirically, this is not in general true for this kind of optimization. But the important thing is that the sign pattern is piecewise constant. Another case where we can analytically show the sign pattern's behavior is if your W is orthonormal. If your weight matrix is orthonormal, then basically you can derive a closed form, an explicit closed form expression for xt star, and involving soft thresholding the transform signal and applying the transpose of the operator. And in this case, you can show that on the Stiefel manifold of orthonormal matrices, the sign pattern, the sign of WX star, is piecewise constant. So if you're doing gradient descent on the manifold, then the sign pattern is piecewise constant, and therefore the implicit closed form expression becomes explicit again. And but in the most general case, it's hard to kind of show that the sign pattern is piecewise constant. But we have empirically kind of extensively checked that the sign pattern, even in the more general case, tends to be constant in neighborhoods of these transform operators. So once your sign pattern is fixed, then you can basically turn your X star, the formula for xt star, into an explicit expression, and you can compute gradients. So your loss function kind of looks like this. This is the L2 loss, and you can take the gradient, apply chain rule, and take the gradient further through X star, and these are the expressions. So now that we can compute gradients, we can design our algorithm. How do we solve this bi-level optimization? Kind of an exact gradient descent algorithm. So we kind of initialize our transform matrices with the identity, and this turns out to be an important initialization compared to random initialization, which we use in neural networks. We found that the identity is a better initialization, and maybe it's tied to sparsity, so that's something to think about. So basically, for every training pair, we would solve the lower level optimization problem to find X star, and from X star, we can find the sign of WX star, And once we know the sign of Wx star, we can compute the gradients because the sign determines the closed form expression for xt star. And from that, we can compute the gradients and update the transform and process another training pair or a batch of training pairs. All of that is possible. So now let's look at some experiments of how this kind of transform learning works. We looked at denoising 1D signals as well as images. And so these are two kinds of one-dimensional signals. One kind is piecewise constant. So these signals would be sparsifiable ideally by the finite differencing operator. And these are kind of smoothly varying signals that are sparsifiable by the discrete cosine transform. So we kind of had a ground truth transform to work with. And then we learned the transforms from these kinds of signals in a supervised way by with noise in the process. And you can see that the learned transforms very closely resemble our ideal ones. There are some differences. In fact, those differences lead to a slightly better denoising performance for the learned transforms because they are learned with supervision. So they are learned for the task. And this is for images. We worked with the Urban 100 dataset where there are many different patterns in the data. So we wanted to see if we can learn different kinds of textures and in our filters. And turns out you can. And then we trained on a set of images and we tested on a different set of images. And this is kind of showing the peak signal to noise ratio for different denoising algorithms. BM3D is sort of a canonical benchmark that people have used for a long time. And analysis KSVD is sort of learning this transform operator. This is from Mickey Elad, who is one of our speakers. And so this is learning the transform operator, but without supervision, directly on the noisy data. And BLORC is our scheme, which learns with supervision. And then after you learn, you apply it for denoising. So what we found is that higher noise levels, the supervised scheme works better. Lower noise levels, analysis KSVD is slightly better because it learns features on the data on the noisy image itself. And if the noise is less, then you can learn the features more reliably. So, and we also looked at how does the transform evolve as you increase the noise. Is there like a phase transition in the behavior of this, of the transform learned in a bi-level way? So what we see is as we increase the noise level in the training data, the transforms is fairly robust to the features are fairly robust to the presence of large amounts of noise. The only thing that changes is the scale of the transform because we kind of removed a regularizer parameter in front of the L1 norm. Instead, the transform itself absorbs the scaling that the regularizer needs, the strength that the regularizer needs. And so, but at some point, basically the features change. So going to very high noise levels, you don't get the finite differencing structure anymore, but it's a different structure that's kind of more appropriate at those high noise levels. So suddenly there's a phase transition in the behavior of the learned filters with this approach. And the last thing is we wanted to compare to some more off-the-shelf solvers for a bi-level optimization problem, like say CVXPy, where we basically computed the gradients with our block scheme, which is sort of an exact gradient, and compared it to numerical gradients. And also did the same for CVXPy. PyTorch here is basically we use our closed form expressions and just computed the gradients with PyTorch. And so block kind of gives you better errors in computing the gradient because it's a closed form expression, and it's also slightly faster. So that's kind of the takeaway. And an extension, so everything we talked about here was with a linear model. And something that we are working on is, or we are interested in is, how do you extend this if you have a neural network instead? So if W is a nonlinear operator, then we kind of know that if we have a ReLU network, it's piecewise constant with respect to the input. So using that property, we could still linearize and use our similar analysis even for a nonlinear setting. So that's something for future work. So that's kind of the first segment of my talk. If you have any questions, I'm happy to take before I move on to more deep learning. So the key takeaway is that having kind of more systematic gradients is helpful rather than doing black box optimization with CVXPy. So for these settings where we have sparsity regularizers, we can learn we can derive the algorithms more carefully, and that can be helpful. So our next part of the talk is going to be on learning without supervision. So there's no training data or very limited training data. And we want to learn regularizers involving neural networks. So the setting is, for the application we'll look at is MRI for this part of the talk. Previous part was image denoising or signal denoising. For MRI, basically, we have a measurement operator. And if you're doing something called like multicoil MRI, you have multiple receiver coils that collect the data. And then so you have, for each coil, you have a corresponding measurement operator and a corresponding set of measurements. And this is sort of the traditional regularized optimization that you would do. Now, so we saw sparsity-based approaches, compressed sensing, and blind compressed sensing is sort of where the parameters of the regularizer are learned while doing the reconstruction. So if you're learning a transform or dictionary, you can learn it from the undersampled data or the noisy data itself. So that's blind compressed sensing. And what we saw just before is sort of learning the same transforms in a supervised way, regularizer in a supervised way. But that was kind of a simple regularizer, right? So we have deep learning that has shown a lot of promise for image reconstruction, MRI, CT, and other applications. Now, but often they require large data sets. So our interest was, can we learn deep priors without any training data? So just from a single image measurements. And this approach is called deep image prior. So basically, a network is learned to predict a reconstruction by just optimizing a data fidelity loss. So if you're doing denoising, the network is trained so that its output fits the noisy image. And that's it. That's the training loss. And once you train this network parameters theta, you pass a fixed input. So the input is typically fixed and randomly chosen through the network, and you get a reconstruction. And you could do the same if you have a more general inverse problem, like for MRI, you can do the same kind of optimization. The key is that the network is learned from the measurements of a single image rather than from a data set. So you have to do this optimization every time you're trying to scan a patient or do something else. But there are challenges with deep image prior. So if you typically the cost is optimized using something like Atom. And the issue is that because you have no training data, there is an overfitting phenomenon that's observed with deep image prior. And because of this overfitting phenomenon, people have proposed various tools to get around it. So what is this overfitting? So if you kind of look at an image denoising problem, so this is kind of a noisy image. I hope you can see the noise. And this is kind of the clean image. So if you focus in the darker regions, I think you can see the noise. So the way deep image prior works is you initialize the network weights randomly, and then you minimize the fidelity between the network output and the noisy image. So as you do the optimization, initially the image output looks like noise, the network output looks like noise, and as you optimize more and more, the network output, the PSNR, the peak signal noise ratio, improves. You get kind of more denoised images. But as you iterate over and over the network optimization, you get really the noisy image in the very end. So that's the overfitting that you get a denoised image at some point, but after some time, it just gives you the noisy image itself. And the same issue comes up if you're doing a more general inverse problem like MRI reconstruction. So you initialize the network randomly, and here we basically undersample the Fourier measurements in K-space. So initially, the network reconstruction looks kind of random because the weights are random, the input is random, the network input is random. But as you optimize the network more and more, you get something that looks reasonable but still very noisy. But as you optimize even more, the PSNR drops, and you get something that's very noisy. Basically, what it's doing is it's adding spurious perturbations in the null space of the measurement operator. And there is no control in the DIP training that prevents adding these spurious perturbations in the null space of the operator. So that's one issue with deep image prior. Another issue is spectral bias. I think there's another talk maybe tomorrow by Madhi who may talk about spectral bias. So spectral bias is the property of deep CNNs that they typically learn low frequency image content much more quickly than high frequency image content. And there has been recent analysis with neural tangent kernel analysis to analyze how this happens, and particularly for signal denoising. And so it also affects the performance of deep image prior for other inverse problems like MRI. So here's an example where we undersample the Fourier space by 4 times. And this is kind of showing the reconstruction with deep image prior of different frequency bands. So reconstruction of the low frequencies, the mid frequencies. So the yellow portion is the frequencies over which you compute the error of the reconstruction. And then high frequencies. What you observe is that the low frequencies are reconstructed very quickly, and then higher the frequencies, that they are reconstructed more slowly. And at the same time, there is also the overfitting phenomenon. If you run more iterations, the errors all go up. So the spectral bias may or may not be a bad thing. So it's in a sense a good thing, because it allows you to capture the low frequencies of the image quickly, and images typically have a lot of low frequencies. So it helps to reconstruct the image quicker than the noise. So in that sense, spectral bias is good. It may be seen as a negative in the sense that you are not reconstructing the high frequencies as quickly as you would like. So these are the issues, and a number of works have tried to address some of these issues with deep image prior. For example, by constraining the architecture of the network, having a lower parameterized neural network to kind of reduce the degrees of freedom during the training, or using additional regularization, or injecting Gaussian noise in the update of the weights, which I think Ima also alluded to, which is sometimes referred to as Langevin dynamics in gradient descent, or by controlling the Lipschitz constant of the convolutional layers of the network. So these are a kind of a splatter of different techniques that people have used to address the issues with DIP, and these mostly focused on denoising, and the improvements are kind of, there's some improvement, but not significant from using these tricks. So we wanted to improve DIP by careful choice of the network input and regularization. And our motivation was a recent work where basically they showed that you can choose a network input that's almost like the image you want to reconstruct, and then magically, or well, maybe expectedly, DIP works really well in reconstructing the image. But the thing was that there was no clear way in which we weren't clear how they chose such an input, right? So, but the way to think about it is, if you have an image that looks similar to the one you're reconstructing, then all you're training the network to do is to transfer the style of the image to something that's more data consistent, more consistent with the measurements that you have collected. So that's sort of this reference-based deep image prior. And in practice, how do you find this reference? If you have a collection of images and you only have like highly undersampled measurements of a patient that you've scanned, then probably the best you can do is get a reconstruction by some existing algorithm and then compare it to your database to find a reference that's similar. So that's what we did in our experiments. And so here's an example of how this sort of reference-based deep image prior works. So this is sort of the vanilla DIP, deep image prior. And clearly it has artifacts that we couldn't get rid of. And we chose a reference. This is from the fast MRI dataset. We chose a reference that's somewhat similar to the image we are reconstructing. And when we learned the weights in the network with this input, it gave a pretty consistent reconstruction. So compared to the ground truth, it's a lot closer. And the choice of this reference has some effect. So if you chose the reference less carefully, then the PSNR, the peak signal to noise ratio drops somewhat. So this kind of seems promising. The other thing was we still don't have any regularization. So what we wanted to introduce was additional regularization, but that's something that could alleviate spectral bias. So we chose our regularization so that it's looking at consistency of the Fourier space of the reconstructions with respect to the references that we have on hand, but only at the high frequencies or only at the complement of the frequencies that were sampled. Typically, the sampling has more low frequencies in K-space. So if you look at the complement of the sampling mask, it will cover more high frequencies. So we thought this is a way to maybe give more preference to higher frequencies in the regularization. So here's kind of the results with these methods, comparing the overfitting spectral bias behavior of vanilla DIP, and then these two other methods. One is using a reference image as input, and the other is with this additional regularization that we introduced in the previous slide. So with these reference-based methods, there's a clear difference in terms of the performance. The reference-based methods perform a lot better because you have some information that you're exploiting compared to the vanilla DIP. And so the overfitting still happens, but it's a little slower and more benign. And if you look at the reconstruction of the low frequencies and the high frequencies, the behavior is, the plots are more benign for these reference-based methods. So the challenge here is that we still assume that we have access to some references, whereas the original deep image prior was designed to work with no training data. So how do we kind of design a robust deep image prior scheme that uses no training data? So that brings us to our what we call self-guided DIP or self-supervised or whatever you'd like to call it, and where basically instead of assuming a known input or reference that goes into your network, we optimize the input along with the network weights. But this has to be done a little carefully. If you just blindly optimize the network input and the network weights, we observed it doesn't work as well. So we had to kind of use our observations from working with references so that if you look at how it works with the references, the reference is somehow related to the ground truth. So you can think of it as a perturbed version of the image you're reconstructing. And somehow the network is able to remove that perturbation at its output. So if we think of that as some kind of denoising, then basically training the network to act as a denoiser by introducing, having some perturbations, that is key when you're trying to optimize the network input along with the network weights. But the thing is, we don't have a reference here, and we don't know what is that perturbation. So we basically ended up sampling these perturbations eta from a distribution, and this could be we didn't see any particular preference for a distribution for those perturbations, but what you can sample from those the perturbations from a distribution, and then we also introduced a smoothing in the end. So you can smooth the network output over different initializations of these perturbations because you don't know what is the right perturbation. And that's kind of also inspired by recent techniques in classification called randomized smoothing, where if you have a classifier that was just trained as it is, if you introduce adversarial perturbations, then the classifier is known to can fail. But randomized smoothing tends to smooth the classifier so that random perturbations or small perturbations do not change the output drastically. So that's coming from the classification literature. And so you can see the output here as sort of a randomized smooth network output. But it's important that we have this sort of denoiser regularization for this method to work. So this is kind of showing the effect of this denoiser regularization. So if you did not have that regularizer, so we just optimized the network input and weights, and we did not have a denoising kind of regularization, then the performance drops quite a bit compared to when you have this regularization. So these are sort of the ingredients that go into our self-guided deep image prior scheme. And so we tested these methods or these improved versions of deep image prior on the fast MRI multicoil knee dataset. And we worked with sort of a supervised, but we also compared with a supervised network. So if we had to do that to see if these schemes can beat a supervised network trained with many images. So here are the results. Actually, we chose a pretty over-parameterized network, and we found that that was necessary for it to work. And so here we are comparing performance for MRI reconstruction at two different accelerations, 4-fold undersampling and 8-fold undersampling, comparing the reference-based methods and the self-guided DIP with the supervised method and the regular vanilla DIP. So all of the proposed methods outperform vanilla DIP, often by several decibels. So there's a clear improvement in performance over vanilla DIP. But the interesting finding was that the self-guided DIP, which learns completely with no training data, adaptive to the image or to the measurements themselves, performs the best. So that is very promising. That as long as we do the deep image prior setup in a nuanced way, that it can give very promising performance, and performance that even beats the supervised scheme that was trained with with a larger data set. And so this is sort of visuals comparing the different versions of deep image prior, the reference-based schemes or the self-guided scheme with the supervised network. And I'm not sure if it's clear, but the supervised network tends to produce some over-smoothing in the zoom-ins, and the self-guided scheme kind of seem to alleviate that effect. And again, these are the PSNR plots and the errors in different frequency bands, low frequency, high frequency. Vanilla DIP has the characteristic overfitting, and the self-guided or reference-guided schemes don't. The self-guided scheme, the PSNR seems to keep continuing to increase. Like, does it just continue to increase? And no, it doesn't. So at some point, it also overfits. There is also overfitting with the self-guided scheme. It's just that it takes more iterations, so it's slower to run. So that wraps up the second portion of my talk on how we can learn neural network regularizers with no training data, basically, for imaging. So if there are any questions, I'm happy to take before going to the last part on building deep networks that are robust. Yes.
Yeah, thank you. So you said you are not sure what was the initialization for deep image prior?
No. The original deep image prior uses a random input and also random initialization.
Yeah, that's true.
Right. So that's what we use for when we compare to the original deep image prior.
Yeah, thank you. That's true.
Yes.
Yeah, so Sai, a quick question. I'm just curious, just correcting if I'm wrong, right? Because I also, when you talk about DIP, one of the issues that really is unclear what is the optimal number of iteration, right? And this self-supervised DIP still doesn't solve that problem, or can I say that?
It doesn't resolve overfitting.
Okay.
It kind of has a more gentle behavior.
Alleviate that kind of things a little bit. Right? Okay.
Yes.
I see. Thank you.
So there are a few things, right? One is overfitting, one is performance, because having no training data, how do you get really good performance? The last thing was spectral bias. So in terms of performance and overfitting, there is some benefit with sort of this the proposed schemes compared to the regular DIP. And the fact that it's doing better than a supervised network is quite promising. So we are working on trying to extend some of the NTK analysis to these other DIP methods, but that's kind of in the works, and hopefully we'll have something in the future. So for the last part of the talk, this is going to be back to supervised learning, but now with deep neural networks. So with deep learning, there are multiple ways in which you can use deep learning for image reconstruction. One category of methods is called image domain learning, where basically from the sensor data that's collected, we would perform an analytical reconstruction. Think of this as a pseudo-inverse applied to the measurements, and you get a sort of a corrupted image, and then a network is learned to denoise this image in a supervised way. So that's called image domain learning. You can do the same in the sensor domain, where if you have artifacts or missing data in the measurements, you can learn a network to sort of remove that. And so that's a sensor domain network. And then you perform a simple analytic reconstruction, assuming the data is now perfect, the analytical reconstruction works very well. Another approach is Automap, which kind of removes the analytic reconstruction step in between and just goes directly from the measurements to the image. And often, and this method requires a fully connected layer in between, or there have been some tweaks of that. So that kind of consumes a lot of memory and computation. The methods that are very popular are these hybrid domain learning methods, where basically there's a neural network, but the neural network is also combined with the forward model or the measurement operator that, or the known physics of the imaging system. So trying to use some known priors about how the imaging measurements are collected together with using networks in the reconstruction process. So this is an example of such a hybrid domain learning method called MODL, or model-based deep learning, where basically the method tries to solve this optimization. So there's a least squares data fidelity term and a regularizer. This regularizer is just trying to just trying to have a network that auto encodes the image. So it's an auto encoding kind of regularizer. And so this reconstruction depends on the weights of this network d theta. So what is done in MODL is an alternating minimization is adopted for this minimization, where basically you kind of introduce a pseudo variable z, which is the output of the network. So you alternate between updating the z and then fixing the z and updating x, which turns out to be just a least squares problem. And so the updating of z turns out to be like a denoising process. So that's the step where the x is fixed and it's passed through this network, and the network serves to denoise the image. And then the next step, the network output is fixed. So this quantity is fixed, and then this loss function is solved with respect to x using conjugate gradients, and that's this data consistency step. And this process is unrolled for several iterations. And then the network is trained end to end with supervision. So this is using sort of the unrolling approach instead of using bi-level optimization, like I talked about in the first part of my talk, which would be the more nuanced way of learning a regularizer rather than with the unrolling. So we'll see quickly what happens because of doing this unrolling. So this is the output of MODL with where the k-space was undersampled by four times. So it's a quarter the data that was collected, and then the reconstruction was performed. And the network was learned with supervision. And what we found is that if we introduce even tiny perturbations in the input to the network, the output can basically collapse. That the tiny input adversarial perturbations can basically destroy the output. And there are other kinds of perturbations to which the network is unstable. For example, if you change the sampling rate, so instead of collecting 4-fold undersampled data, if you collected 2-fold undersampled data, so you're collecting twice more data, then the network just fails. Or when you're doing the unrolling, instead of unrolling for 8 iterations of the alternating optimization, if you unroll for 16 iterations at testing time, again, it fails. So the unrolled deep network is really unstable to a variety of perturbations. And so the question was, how do we alleviate this lack of robustness in the deep network reconstruction? Right. So, and I mentioned adversarial perturbations, and you might be wondering how is that related to image reconstruction, because the most common scenario you might have heard about it is for image classification. In fact, I think there's a talk tomorrow about it. So in the image reconstruction setting, think of the imaging measurements that you obtain, and those measurements go into a reconstructor. So if you may be able to find perturbations of those measurements that would basically cause the reconstruction to diverge from the target image. And those kinds of perturbations would be adversarial perturbations. They could be really small perturbations, but if they are adversarially chosen, they can cause your reconstructor to fail. Another question would be like, well, these adversarial perturbations or adversarial attacks may make sense for classification because there may be an attacker trying to fool your network. But if you're in an MRI scanner, nobody's going to attack you, right? So, but it's sort of it's not the fact that it's an adversarial perturbation, but the reconstructor could fail even with small perturbations. That's concerning. So for classification, many methods have been proposed to address the lack of robustness of deep neural networks. But these approaches are much less developed for image reconstruction for inverse problems. So in sort of our work, we proposed a way to make a deep unrolled network more robust by integrating this technique called randomized smoothing, which I alluded to in the second portion of the talk. So randomized smoothing, so this is sort of what we would call as end-to-end randomized smoothing, where basically X is the input to a reconstruction network, and F denotes the unrolled network like MODL, or it could be any deep neural network. And so typically we would just pass the input through the network and get the output that's our reconstruction. But with randomized smoothing, what would be done, is you perturb the input to the network by some perturbation nu that's drawn from a distribution, and you average the output of the network over this distribution. Or basically, this leads to a reconstruct that's a smooth reconstructor. It's basically trained to handle all these perturbations. And this is a trick that's been used for classification, but recently there's also interest in doing this for image reconstruction. So an end-to-end randomized smoothing process would basically take the MODL network, which is unrolled for several iterations, and then pass a sort of perturbed inputs to this network, and then average the outputs that come at the output of the network. So, but it's not clear if this is the way to do randomized smoothing. The question in your mind should be, what are the components of the network that are robust? What are the components of my reconstruction network that are not robust? Let's try to understand that first, and then we can see which components we need to make robust. So that was kind of our research question. That is, where should this randomized smoothing kind of robustifying operation be introduced in a deep unrolled network architecture? And then how do you train the network in the presence of this randomized smoothing? So for the first question, our choices were kind of obvious. We are kind of unrolling this alternating optimization with a denoiser and data consistency many times. So we just looked at end-to-end smoothing, which is smoothing at the output of the network. We could introduce smoothing at every iteration of MODL. That's an option. That is, after every denoising block and data consistency, you could do an averaging so that you introduce noise here at every block, and then you average the outputs after these two, basically an iteration. That's one option. Another option is to do this only for the denoiser, because the data consistency block that's basically a physics-based block, right? That there's no neural network in there. So an alternative would be that have it only in the denoising block. So those were the two options that we considered, and then the question is, how do you train the network with this sort of randomized smoothing operation built into it? So what we adopted was sort of a more common approach now in computer vision, which is pre-training and fine-tuning. And so the pre-training we did was basically take the network in MODL and train it to be a denoiser, just a denoiser. So basically you have a set of images that you can simulate noise, add it to these images, and then train the network to be a denoiser. And then once you have this pre-trained network, you can fine-tune the weights. And so the fine-tuning loss has two portions. One is a typical supervised loss. Basically, you have this network with the randomized smoothing built into the network. And so you look at the output of this randomized smoothed MODL and compare it to sort of your target or ground truth and minimize the error. And that's basically supervised loss. And then we also had this important additional term, which is an unrolled stability loss. So basically, at every iteration of MODL, we are passing perturbed inputs. So xn is the output of MODL at the nth iteration, and we add some perturbations nu or noise, and we pass, and then we sort of do an averaging of those, right? So what we did was we want the output of the network with these perturbed inputs to match the output when the target or ground truth is passed through the network, because we are trying to train the network to be an autoencoder. So that these perturbed network inputs should match what you would get if it were an autoencoder, which is sort of the image, the target passed through the network itself. So this we call kind of the unrolled stability loss, and we had both of these components to kind of fine tune the weights of our network once we pre-trained it. So basically we tested out the our smooth unrolling scheme on the fast MRI dataset, and we tested it with a variety of perturbations. So one was with sort of an adversarially chosen perturbation. So that's sort of the what's here as robust accuracy, where we basically for every testing case we chose a small perturbation but adversarially chosen. And then we also tried more realistic perturbations, just Gaussian noise or random noise added to the inputs of the network. So what we found was that compared to vanilla MODL, which is not trained to be robust, which doesn't have this randomized smoothing, the randomized smoothing based methods, so this is the end-to-end smooth network. This is SMUG, which is our scheme, but with this is the smoothing is done after every iteration. And this is smoothing that's done only at the output of the denoising network. So what we found is that the SMUG with just the smoothing done for the network output is a lot more robust in the presence of both random noise as well as adversarially chosen noise compared to all the other methods. So there is a level of robustness that comes in with incorporating randomized smoothing. And this is kind of showing plots behavior of our algorithms with different kinds of perturbations. So here we are just adding the perturbations or these noise perturbations to the input of the network and increasing the strength of those perturbations. So as you increase the strength of the perturbations, basically the regular vanilla MODL fails, and even the end-to-end randomized smoothing fails. But if you incorporate randomized smoothing in sort of in a more systematic way inside the unrolled architecture, that seems to give you more robustness than these other methods. The second plot is basically looking at what happens if you change the sampling rate at testing time compared to training time. And again, we found that with SMUG, the image reconstruction is quite robust when you change the sampling rate compared to the other methods, vanilla MODL or even the end-to-end randomized smoothing. And this is showing what happens if you train with 8 iterations of MODL and then at testing time, you unroll for many more iterations, right? So the vanilla MODL is known to fail when this is done. Basically, if you just unroll for a few iterations and train the network, it doesn't work if you run the whole optimization for many iterations at testing time. It just, so that the PSNR just drops. But if you introduce the randomized smoothing into the process, the reconstructions are relatively stable, even if you run for enough iterations. So, although the network was not trained to be robust to these perturbations explicitly, just introducing the randomized smoothing into the unrolled architecture provides automatically a level of robustness against a variety of perturbations. So here is sort of a visualization where this is the ground truth, and we had perturbations in the input. With vanilla MODL, you can clearly see artifacts arising in the output because the network fails in the presence of the perturbations. And this is with end-to-end randomized smoothing, which seems to alleviate a little bit the artifacts, but they're still there. And then with the proposed SMUG approach, you see pretty much the artifacts have cleared up. So it's more robust to perturbations. And these could be not just perturbations, these could also be distribution shifts between the training and testing data that one would need robustness for. And I think tomorrow one of the talks is, I think by Dr. Heckel is handling this. He's going to be talking about this issue of distribution shift. So that's pretty much it for the talk. So to summarize, I started off with talking about learning sparsity regularizers for inverse problems in sort of a bi-level optimization framework. And so I kind of said that this is a more preferred approach than kind of doing unrolling or other relaxations for learning regularizers. And then we switched on to learning deep neural network-based regularizers and with no training data. And then we switched back to doing supervised learning of networks. But then we looked at how do you make the supervised learning more robust to different perturbations or changes in the experimental settings that would be crucial for things to work for imaging applications. And there are a number of different future directions possible. NTK analysis for our deep image prior schemes, analyzing the robustness of the SMUG approach more theoretically, and so on. So these are directions that we hope to continue to work on. And I would like to acknowledge our NSF grant with Ching and the ARS Foundation for the medical imaging support. And that's it. Thank you. Happy to take any further questions. Yes.
So I want to ask again about initialization. Did you try random initialization?
For which method?
For the MRI.
Random initialization of network weights?
Yes. No, the latent space.
Random initialization of the... Well, we typically started with random initialization for the network weights. For the, if you're talking about the input, that depending on DIP, or we had different choices for the network input.
Okay, so you didn't try random input? We
did. So okay. For the what I call vanilla DIP uses a random input to the network.
So which one is better, the random one or the one that you have an image?
Yeah, it's the other one. So if you have an image, whether it's a carefully selected image, a reference, or if it's self-guided, if it's optimized, the image is optimized, both of those seem to do better than assuming a random input to the network.
Okay, thank
you. In a sense, when you have the reference, it kind of makes the problem a little easier because the network knows something about what the image looks like, and it's just trying to learn what's new that's sort of consistent with the data that's collected. That's a way to think about it.